Alrighty, welcome back to another help video. Today we'll be talking about Kepler's third law. So Kepler's third law is a law that describes how planets move around the sun. Specifically, how far away they need to be from the sun to take a certain amount of time to orbit around the sun. Now, it is important for us to remember, planets do not orbit in perfect circles. They orbit in a shape called an ellipse. Now, this is a very exaggerated ellipse, okay, or an oval. But planets orbit in these ellipse shapes. They are not perfect circles. In an ellipse, you usually have two focuses, like so, where one of them is the star and the other is some random point in space. So this also means that your planet will get closer or further away from the sun depending on where it is in its orbit. If we say this is the sun right here, our planet is going to be a lot closer to the sun here than it is all the way over here, for example. So distance is not constant, and according to Kepler's second law, neither is the velocity or speed that we go around. As we get closer to the sun, we speed up. These are just general important things to remind ourselves of in terms of the concepts that are going into what is happening here. But we're going to mainly focus on the math. And in order to do that, we're going to do two examples. So let's do that. So, two examples. Our formula is written on the whiteboard here. P squared equals A cubed. Now, what does that equation mean? P squared equals A cubed. P is our orbital period. This is going to be measured in Earth years. Okay. Now, if I get this thing to stop tracking me for a second. There we go. P is going to be Earth years of an orbit. Okay. So that's how long it will take for the planet to orbit the sun in Earth years. A is the average distance between the planet and the sun measured in astronomical units. Remember, one astronomical unit is the average distance between the Earth and the sun. The reason why we use astronomical units is because, or not the reason why we use astronomical units, the reason why we talk about averages here is because our distance is never constant, okay? Throughout the year, we are changing how far away we are from the sun at all times. So we had to take an average here. So we're going to do two examples, one in which we solve for P, one in which we solve for A, to make sure that we know how to do both of them. So let's start off with the planet Saturn. Now, Saturn is known to have an average distance away from the sun of 9.5 astronomical units. So, because it's astronomical units, we automatically know A is equal to 9.5 AU. And we know it's A because astronomical units is a measurement of distance. I don't know P. Okay, P right now is unknown. But we want to be able to solve it. And we know for a fact our formula is always going to be P squared equals A cubed. Now, for those of you who may be watching this who aren't my students, you may see this rewritten as P squared equals A cubed divided by M, where M is the mass of the star that we're orbiting. For our purposes, we are only dealing with the sun. Since we measure that M in solar masses, it would be A divided by 1, meaning it's just A. If we were dealing with other stars, we would have to take into account their mass. But this simplification of this formula works very well for the sun. So let's go ahead and try this out. Okay, plugging into our formula, P squared stays as P squared because we don't have anything for that yet. But A gets subbed out for 9.5. Now notice it's A cubed in the formula, so I had to make sure it's at 9.5 cubed. Okay? Whatever's happening to A in that formula has to happen to whatever value is represented by A. So, at this point, I have a variable being squared and I have a number being squared. The easiest thing for me to do at this point is to simplify this as much as possible. P squared can't really be simplified yet. Okay, that's just something that I would have to solve for later. But 9.5 cubed is just a number. I don't know what that number is yet, but I can use a calculator to figure it out. So I'm going to take a calculator, and I'm going to do 9.5 to the power of 3. So I'm going to find where my cube button is, or if I don't have a cube button, then I'm going to just do the number multiplied by itself 3 times. So 9.5 cubed. When I do that out, I get 857.375. So I rewrite my equation. P squared, I didn't do anything to. So that stays here. But 9.5 cubed, I did do something to. I simplified it. I did 9.5 cubed. And that came out to 857.375. Now at this point, you may be tempted to say that you're done. Okay? After all, we have P by itself and we have a number. Therefore, that should be it. But this isn't P. This is P squared. We need to just get P. So we need to undo this square somehow. The way that we do that is by taking the square root of that. So, similar to squaring something, taking a square root is the exact opposite of it. So, if I take the square root of P squared, I'll be left with just P, which is what I want. Okay, that's what my final answer is going to be. However, anything I do to one side of my equation, I have to do to both sides. So I'm also going to take the square root of 857.375. So I'm going to find that button on my calculator. I'm going to hit it. And when I do, I get 29.28. Mind you, I'm rounding there, okay? There's a bunch of other numbers and all that after that. Okay, a little bit of number garbage there. But for our purposes, 29.28 is good enough. The last thing I need is my unit, okay? This number right now has no meaning to it because it doesn't have a unit, okay? I need to give it meaning. I need to define it. The way that I do that is by understanding what did I actually just solve for. I solve for an orbital period. I know for a fact that this formula will give me orbital period in Earth years. So therefore, P is equal to 29.28 years. And that would be my answer. So again, all I did was I cubed whatever number was given to me, and then I took the square root of that number. And when I did that, I got my final answer. So that is how you solve a Kepler's third law problem if you are given the distance. Now, let's go over how to solve a problem if we were given the period. Okay, so I'm going to go ahead and erase this. Okay, we're going to get out of the frame for a second if anyone needs to, check that real quick. Well, actually, you know what? We actually just keep that there because we will actually just move over here. So I believe it's this symbol. So we'll just move right on over here for now. Actually, no, we'll just move over here to an area where we have some white. There we go. All right. So now we're going to worry about Jupiter. Okay. Now Jupiter is closer to the sun than Saturn. So realistically speaking, our answer when we solve for A should come out to be less than 9.5 AU. Because that's the average distance between Saturn and the sun. So we should get a smaller number than that. I'm given that P is equal to 11.86 years. I do not know A. And again, my formula is P squared equals A cubed. Okay? So, same as before, I'm going to plug in, right? I have my variables here, okay? I have only one unknown variable, so I'm going to go ahead and plug in here. So p squared, I know the value of p now, so that becomes 11.86. And since p is being squared in the formula, whatever value p is has to be squared when we do the actual math out. So this is going to be 11.86 squared. Okay? I'm also just going to make a little line there so that we can see there's a difference here. Okay? That is going to be equal to a cubed. Now, a, we don't know what it is yet. So therefore, that just stays as a cubed. Now, similar to before, we have a variable with an exponent that we can't really do anything with yet. And we have a number with an exponent that we can do something to. So let's take care of the number first, because that'll be easier for us in the long run. So I'm going to do 11.86 squared in my calculator. So I'm going to clear that out, and we're going to do 11.86 squared. Okay. At this point, it's pretty important that you're pretty familiar with how to use your calculator. Okay, you should know where the square button is, where the screw root button is, how to take a cube root, and how to cube something on your calculator at this point. If you don't, then you should probably be doing a little bit more practice with your calculator. Or you should stop using multiple different types of calculators. That way you know how to use one specific type. Either way, when I do that out, 11.86 squared comes out to be 140.66, about. So 140.66. Okay, give or take a little bit. That is going to be equal still to a cubed. We can't do anything to that yet. We didn't do anything to it yet. So that just stays there. Now, same story as before. You may think that you're done here because you're left with a variable and a number. You're not done yet, though. You do not have a yet. You have a cubed. Okay? We need to take the cube root of this. Okay? Noticeably, this is different than the square root. Okay? It is a cube root. Notice there's a 3 in there now, right? So we must take that cube root. Again, there should be a function automatically in your calculator somewhere to be able to do this. If you are unable to find it, a different trick that you can use is instead of taking the cube root, you can do it to the power of 1/3. That is mathematically identical. But thankfully, the calculators that I have in my classroom right now do have a cube root function on them. So I'm going to go ahead and I'm going to do that. And when I do that, I'm left with a number. Okay, so a now by itself is equal to 5.2. Now, again, there is something wrong with this number. There is no unit on it. Without a unit, it is meaningless. There is no definition to the number. So I need to apply a unit to it. I know for a fact that there are only 2 different types of units that I'm dealing with when it comes to Kepler's third law. I'm either dealing with years for an orbital period, or I'm dealing with AU for a distance. This, I know for a fact, is a distance because it's A. So therefore, my final answer, 5.2 AU. And a good way to make sure that that makes sense, I know for a fact, if this thing would like to start tracking me again, there we go. I know for a fact that Saturn has an AU of 9.5. Okay, 9.5 AU is Saturn. So I know that whatever number I get should be less than 9.5. Last time I checked, 5.2 is in fact less than 9.5. So therefore, my answer checks out and makes realistic sense. Okay. Additionally, my orbital period should be less for Jupiter than it should be for Saturn. For Jupiter, I know for a fact my orbital period is 11.86 years. For Saturn, I calculated that it was 29.28 years. Again, this checks out. This makes sense. So when you're doing these problems, it's important to not only just do out the calculations, but also understand what the calculations mean. If you don't understand what they mean, there's no point in doing the calculations in the first place. So, with that being said, this concludes today's video. I hope you found this helpful. Make sure to smash that like button. Make sure to subscribe and ring the bell so that you're notified with any future uploads. And as always, I will catch you all in the next video. Thanks so much for watching.